Hello again. We're looking at the new material in Math 120. We're now in Chapter 8, and the first new topic we encounter is in Section 6 on rational exponents. Remember that a rational number is just a fraction, so when we say rational exponents, we're basically talking about exponents that are fractions. Now, before we get started, and before we do anything fancy, let's remind ourselves that we already know how to simplify a lot of rational exponent questions. And we know that because we've been dealing with higher power indices. So before we get too far away from where you've been as you've worked through your homework in Chapter 8, let's remind ourselves of a question that we have seen earlier. So here's a question. This is the fourth root of x to the 24th power. And you know exactly how to solve this. You ask how many factors of x to the fourth there are inside of x to the 24th. You're basically looking at the exponent, 24, and the index, 4. And you're saying, since the exponent is bigger than the index, that some are going to get out. They're going to get out 4 at a time. Well, that's exactly the definition of division. If I take 24 and I divide it into groups of 4, we're simply dividing 24 by 4. So that's exactly what we're doing. Now, that means that when we do that, 4 goes into 24 6 times, we can simplify this in exactly the way you'd expect. The fourth root of x to the 24th is nothing more nor less than x to the 6th. Now, that seems perfectly reasonable. It's just asking how many x's get out when they get out 4 at a time. In other words, when it takes an x to the 4th to undo the fourth root of that x to the 4th. And there are 6 groups of 4 in 24. So we could have shown that division. In other words, we could have done this in Math 100. We would simply have said that this becomes a quotient. The exponent is 24, the index is 4, so we take 24 and divide it by 4 and we get 6. So before you get too far into this, remind yourself of the homework you've already been doing. Remind yourself of the fact that when you've got big exponents, you simply divide them by the index. So we're already 3/4, 7/8 of the way to thinking about rational exponents when we deal with simplifying exponentials, even in Math 100. Now, that said, we're going to introduce a definition. We're going to say that the nth root of x is x to the 1 over n. In other words, the denominator of your rational exponent becomes your index. So let's look at our first example. 32 to the 1/5 power. So there's a 1/5. The numerator is 1, so our exponent's going to be 1. Well, anything to the first power is itself. The denominator is 5, and that denominator is going to become our index. So we're talking about the 5th root of 32. Well, that all of a sudden becomes an easy question. The 5th root of 32 is 2. Since 2 to the 5th is 32. All that's saying is that we're undoing multiplying 2 by itself 5 times. 2 to the 5th is 32. When we undo that by taking the 5th root, we get back to 2. Now, this is one that might concern you, because the first thing that you might notice is that there's a negative. And then you'll notice that that negative is not in parentheses. And remember, we can subtract exponentials. So we could subtract 81 to the 1/4 power. So when you think about it that way, remember that exponents are very high on the order of operations, which means that they're going to go before any sign changing that comes from a negative sign. So that negative sign is going to wait its turn. That's going to happen after we take 81 to the 1/4 power. This is an order of operations question. Exponents happen before multiplication. Now, if I wanted to raise negative 81 to the 1/4 power, I'd have to put it in parentheses. And you remember that from Math 100 and earlier sections in Chapter 8. So this is really asking us to do two things. Raise 81 to the 1/4 power and then change its sign. Well, remember that a fractional exponent, the denominator, in this case that 4, becomes the index. So this is a negative, and that negative is out front. It's waiting its turn. This is negative 4th root of 81. Now, of course, the 4th root of 81, the square root of 81 is 9. The square root of 9 is 3. And there's that negative out front, waiting its turn to make that 3 into a negative. And this works just as well with fractions. So if I have parentheses, and there's a lot of stuff in parentheses in this next example. We've got a negative in parentheses, and we've got a fraction in parentheses. So this is, the parentheses are basically telling us that everything is being raised to that 1/3 power, which of course means that we're taking the cube root. That's just a way of saying the third root. Just like we say x cubed, when we undo that, we say the cube root of negative 1/27. Now you can take the cube root of a negative, right? Because a negative times a negative times a negative, and I said that 3 times, is still negative. They go away 2 at a time, but if you've got an odd number of negatives being multiplied together, it stays negative. The cube root is asking us for an odd number. It's asking us for 3 things that are multiplied together that give us negative 1/27. So when we look at that, we can do exactly what you'd expect. We can take the division that was inside, outside. We can take the negative sign that was inside, outside. So I'm going to do 2 things at once here. I'm going to take the division and the negative outside. And then we've got a much simpler question. In the numerator, just the cube root of 1. Well, that's equal to 1 because 1 times 1 times 1 is 1. And the cube root of 27 is 3 because 3 times 3 times 3 is 27. Now, I will remind you that this trick of taking negative signs outside only works when the index, that is the root that we're looking at, is odd. So that cube root, 3, is an odd number, so therefore we can take the negative outside. Now, when you look at the next example, we've got another negative number. We've got negative 6 being raised to the 1/2 power. Now, the parentheses tell me that it is, in fact, the negative 6 being raised to the 1/2 power. Compare that to the question right above it. When we did the question right above it, notice that that negative was not part of the base because there were no parentheses to force it to be. Right at the beginning of the semester, we went over the uses of parentheses. So when we look at this question, that 1/2 power is going to apply itself not just to the 6, but also to the negative. That's going to give us a square root. The index is 2. And that's going to give us trouble because the square root of a negative is not real. It's not a real number. Doesn't live on the number line that you had in a Math 100 class. Now, pretty soon, we're going to talk about what happens with the square roots of negative numbers. And we're going to say that then an I pops out because mathematicians got to name this. We decided to call it imaginary. So when engineers use this, when electronics folks use this, they have to call these numbers imaginary, even though they're tremendously useful. And you'll see imaginary numbers in Marcus de Satoy's documentary. So just a reminder that pretty soon in Chapter 8, Section 8, we're going to say that the square root of negative 6 is I root 6. That I makes this an imaginary number. That doesn't make it any less useful. It's just the name that we've given it. Now, what can we see from our definition? We can see from our definition that we can have an exponent mixed into this. We can have an m there, because if we're simply saying that the index becomes the denominator, then any exponent, there's that m following through, simply becomes our numerator. So the numerator of the exponent is the exponent, and the denominator of the exponent, as we've just seen in the previous 4 examples, becomes the index. And it might be more helpful to say this in words. So here it is said in words, and that's what I've basically just said. So we can also kind of mix math and words and symbols all up in one pot. So there's the index, that's telling us what root to take, and that's becoming the denominator of the exponent. While the exponent itself is simply the numerator of the exponent. So we can follow that through in words as well. And that allows us to really get to our topic, and our topic is, of course, rational exponents. And rational numbers have numerators and denominators. So here we are looking at simply rewriting stuff. So we may not be able to accomplish that much in the next few steps. And in fact, our answers may, to some purposes, be considered wrong. But we're simply going to translate them. We're going to make rational exponents into indices and exponents. Notice there's no parentheses in this next question. So that 14 is not part of the base. The base here is simply x. X is the thing that's being raised to those powers, and that's because of the order of operations. Remember, there's two operations here. There's multiplication going on between the 14 and the x, and there's exponentiation going on between the x and the 2/3. And no surprises, exponents come before multiplication. That's the order of operations. So the 14 is like that negative sign that we saw on the 81 earlier. It's going to wait outside, right? It's not part of this rational exponent. The 3 in the rational exponent, that's a denominator. That's going to become our index. So no great surprise, what we've got is 14 outside. That's being multiplied by the cube root of x squared. We're simply using the definition of rational exponents to rewrite it in a different way. Now let's take a look at this next example. We've got a negative exponent, and we already know how to deal with negative exponents. In Math 100 we saw that if we've got a negative exponent, it means that the base is in the wrong place. So right now that x is in the numerator. It needs to be in a denominator. It needs to go downstairs. So let's do that first. Let's take it downstairs. So that's 1 over x to the positive 5/7. So all we handled in that first step is the negative exponent. That negative exponent tells us that the base is in the wrong place. Because our base was in the numerator, it's now in the denominator. So several pages of your workbook and lots of homework about that. But we still have a fractional exponent. And when we look at it, we see that we even have a denominator. That 7 downstairs is going to become an index of 7 for our radical. Now, I said that sometimes our answers aren't right, and maybe that's not the correct thing to say. Maybe they're just not complete. Not too long from now, we're going to look at a question like this, and we're going to say that that is not the answer, that you cannot have a fraction that contains a radical in the denominator. You can't have a radical downstairs. And that's, of course, a topic for rationalizing. And so we'll address that. But for now, we're simply translating from fractional exponents to radicals with exponents and indices. Now, you might say, what on earth does this achieve? I mean, where are we going with this? So let's actually find a question that gives us some insight into what we're accomplishing here. So in this next example, we've got some fairly big numbers. It's not the 27 I'm looking at. It's the 5 and the 15. And I also notice 5 and 15 are on the same row of the multiplication table. They've got 5s in common. And that fractional exponent business is going to allow us to simplify this really quickly. Now, you might say we don't have enough 27s, enough of those bases, to get out because they get out 15 at a time, and we've only got 5 of them. So in terms of Math 100, we're kind of turning this question on its head. There aren't enough of the bases to get out. We'd need 15 of them for even one 27 to get out. So we're going to rewrite this with fractional exponents, and no great surprise, the index is going to become our denominator. So the first thing you're going to see is 27 being raised to a fraction. The exponent's 5, the index is 15, that gives us the fraction 5 over 15. And instantly you can see the value of rational exponents. 5/15 simplifies to 1/3. 1/3, well, that's much nicer. 1/3, well, I don't even really have an exponent there because it's 1. The index is 3. That's telling me that I'm going to take a cube root. So in the next step, we take the cube root of 27. And you say, well, that is a Math 100 question. That's asking what undoes the cube. and that cube must have been of 3. 3 times 3 is 9. 9 times 3 is 27. So all this works out to nothing more nor less than 3. Now, as many times as you can, it's good to get a reminder that exponents get along great with multiplication. We've seen an example not too long ago where we were able to use the rules for multiplication and division to bring the multiplication outside, to bring the division outside of a radical. But that does not work for addition and subtraction. It does not work for sums and differences. So in some sense, this next question is a trick. It's a trick because when you first look at it, you see the cube and you see the cube root, and you think, well, that's interesting. The cube undoes the cube root. And you see a 27, and you were just reminded that the cube root of 27 is 3. And so you say, well, maybe that's going to be part of this question. But all of that is kept apart, and it's kept apart because of the order of operations. That subtraction means that when we simplify this, when we rewrite this as a radical, the index, that 3, is not going to be able to see the exponent, the other 3. They're kept apart, oil and water, by that subtraction sign. Now let's also notice those parentheses. Those parentheses are telling me that the entire difference, that is the result of performing subtraction, is being raised to the 1/3 power. So all I can do here is rewrite this as the cube root of that difference, x cubed minus 27. I cannot do any more. Multiplication and division pass through radicals perfectly. You can bring them in, you can pull them out, you can do all sorts of stuff with multiplication and division and exponents. You cannot do that with addition and subtraction. So our answer is just that. It's 2 cubes separated by subtraction, and because of that subtraction, the order of operations never allows the cube root to see those 2 cubes. And there's our answer. Now, you might say, well, what can you do with this? And you can do some pretty interesting things. So similar to the question above it, we can look at an example with big exponents and, relatively small indices. And clearly some x's are going to get out. When I perform that division, when I divide, 16,571 by 4, there's a lot of groups of 4 in there. So I'm going to get out a calculator and do that division. And what I see is, when I do that division, that 4,142 groups of 4 come out. So there's our new exponent. And 3 are left behind inside of the 4th root. So it's kind of exactly what you'd expect. We rewrite it using the definition of rational exponents. Then we actually do the division. We see that the quotient is 4,142. We see that the remainder is 3. On a calculator, that would probably be shown as 0.75, which is 3/4. And so we take that 3/4 and we rewrite it as, well, 4 is the index, so there's that 4 out front. And 3 is the exponent, so 3 is the exponent inside the radical. So let's do a similar question to this, a similar question to the question involving the 27. Let's do a question like this with 7s and 21s and x's. So really, in that previous question, we did a lot of work with the exponents before we did any arithmetic. Now, in this question, we're probably not going to do any arithmetic with the x because we don't know what x is, but we can certainly do arithmetic with the exponent and the index. So we're going to rewrite this exactly as you'd expect as a fraction. So that means that the exponent, 7, is being written over in a fraction where the denominator is 21. And both 7 and 21 are on the 7 row of the multiplication table. We factor out the 7s, and we're left with 1/3. So that 1/3 says that the index is 3. So there's our index of 3, and we're taking no more nor less than the cube root of x. We didn't do any arithmetic there. We simply simplified the exponent and the index, but we were able to get a much nicer answer as a result. Now, here's an interesting example of using rational exponents to do something that in Math 100 you might be absolutely convinced you could not do. So take a look at this. First off, that first radical is a cube root. That's the cube root of 5. And we're multiplying that by a square root, the square root of 7. And those indices are different, and you're told by your Math 100 professor correctly that you cannot bring the multiplication inside here because the indices are different. And so you might think, well, there's nothing we can do with this. But fractions can be rewritten with a common denominator, just like when you add and subtract them. And that's exactly what we're going to do. So arithmetic here is going to allow us to do something pretty extraordinary. So the first thing we're going to do is we're going to use the definition of a rational exponent. So because that first index is 3, we're going to write that as 1/3, and the second index is 2, so that'll be 1/2. So we're going to rewrite this as 5 to the 1/3 times 7 to the 1/2. And you might say, well, you can't do anything with that because the denominators are different. But imagine if you were adding 1/3 to 1/2, and we're not really doing that, but it is exactly the same set of steps. We need to get a common denominator, a common multiple of 3 and 2, and of course that's 6. So we make the 1/3 into 2/6, we make the 1/2 into 3/6, and now we've got a common denominator. We're not going to add those, but we've got a common denominator of 6. In other words, just by doing a little arithmetic, treating these like fractions, we now have two denominators that are the same. Now, that means that we can bring that 1/6 out. We can write this as a 6th root. And of course, the exponents stay exponents, so we still have the 5 squared, and we still have the 7 cubed. They're still being multiplied, but now they're being multiplied inside the radical. So in a sense, we were able to bring the multiplication inside, but only through this extraordinary process of making a common denominator, because of course a denominator as a exponent is a index. Now, it's a simple enough matter. You get out your calculator, 5 squared times 7 cubed, and that's the number inside. So we were able to perform that multiplication. This was a multiplication question. And in Math 100, we wouldn't have. We would have simply stopped and said, nope, our rule for bringing multiplication inside does not work when the indices are different. But because we've got fractional exponents, we can bring the multiplication inside. Actually do it in this case. 5 squared times 7 cubed. Now, that's pretty cool, but we can do that even if we don't have numbers. So in this next example, take a look at what we've got. We've got a 6th root, and we've got a cube root. And so we cannot bring the multiplication inside as written. So instead, we're going to do exactly what you'd expect. We're going to rewrite both of these factors with fractional exponents. So those indices are going to become the denominators. So I'm going to see 6ths and 3rds. And then we're going to play the same game. We're going to pretend that we were asked to add 5/6 to 2/3. And pretty clearly, we can make that 3 into a 6 if we multiply that second exponent by 2/2. So that'll become what, 4/6? So when we do that, we have a common denominator, just like before. That common denominator is 6. So we can see that both of these are inside of a 6th root, which means that we can bring that multiplication inside. We can write this as a single radical with x to the 5th times x to the 4th inside. Now remember, when you're multiplying exponentials, you add the exponents, assuming the bases are the same, and here the bases are both x's. So we can add that 5 to the 4, and we get the 6th root of x to the 9th, which is not done. We can do some more with that. So just finishing this up, we can see that we can now go back to a fractional exponent. We can take that exponent of 9 and we can rewrite it with a denominator as a denominator. So we're saying that we're taking the 6th root, So the 6 goes into the denominator, our 9 is our exponent, and 9/6 simplifies. We can factor a 3 out of both. 3 times 3 is 9 in our numerator, 3 times 2 is 2 in our denominator. And then we can use the definition again. That 2 in the denominator is our index, so we're talking about the square root. But notice that we don't show the 2 in a square root. It's the understood exponent. So we're just going to write this as the square root of x cubed. We don't have to show that 2 there. Here's another extraordinary thing that we can use the definition of fractional exponents for. So here's an x inside of a fourth root, a cube root, and a square root. There's 3 radicals there. And of course, this is inside out, the way radicals work. So the first thing happening to that x is that it's being fourth rooted, then cube rooted, then square rooted. So when we rewrite this with parentheses, the innermost set of parentheses are going to have to deal with that fourth root. So the innermost set of parentheses are going to be the 1/4 exponent, and then the next set of parentheses dealing with the 1/3 exponent, and the outermost set of parentheses dealing with the 1/2 exponent. And then you remind yourself of the rules for exponents. When one base is raised to several exponents, you multiply them. Multiplication's commutative, so the order we multiply these in doesn't matter all that much. We're basically talking about multiplying 1/4 by 1/3 by 1/2. Well, multiplication of fractions is the easy one. You just multiply the numerators across and multiply the denominators across. And when we do that, we get 1 times 1 times 1 is 1 in our numerator. 4 times 3 is 12. 12 times 2 is 24 in the denominator. And then we can take this back to the radical form. We can rewrite this with a 24th root, where our index is 24. So all those radicals, the fourth root, the cube root, and the square root, gave us a single radical with an index of 24. Now, 2 more examples where we're going to simplify. So just using our rules, our distribution, and how we deal with negative exponents and things like that. The first one looks pretty nasty, and that's just because of those fractions and the negatives and all that good stuff. But let's remind ourselves that we're multiplying by a difference, right? That subtraction inside of the parentheses tells us that we're essentially going to distribute. So the 4 times x to the 5/3 is going to get multiplied by both terms in parentheses. So that's the x to the negative 2/3 and the negative 4x to the negative 5/3. So when we distribute these, remember what's going to happen. We're going to add the exponents. When you multiply and each exponent has a base, you add the exponents. So in the first terms, when we multiply them together, we're just going to be adding 5/3 to negative 2/3. Well, that's going to give us 3/3. Now, when we distribute into the second term, the 4 in the outside factor is going to get multiplied by the negative 4 inside. A positive times a negative is a negative. 4 times 4 is 16. But look at what's going to happen to the exponents when we add them. When we add 5/3 to negative 5/3, because remember we're multiplying and each base has an exponent, when we add these, we're going to get 0. So that new exponent is going to be x to the 0 in that second term. And this simplifies just beautifully. 3/3 is another name for 1. So that first x to the 3/3 is simply going to become an x. And x to the 0, well, anything other than 0 to the 0th power is 1. So that's just going to give us that negative 16 for the second term. So this simplifies really nicely. No negative exponents, no fractional exponents. And of course, I chose the example to illustrate that sometimes these kind of collapse in on themselves. Okay, one more example, and we are done with our introduction to fractional exponents. And in some sense, it's a doozy. There's negative exponents all over the place. There's fractional exponents all over the place. Notice that one of the exponents is not negative, so that exponent on y in the denominator. But everything else is negative, which means it's going to move. So, for example, the 2 to the negative 2 power is going to go downstairs. The x to the negative 5/8 power is going to go downstairs. Basically, if it's got a negative exponent, it's in the wrong place. So everything with a negative exponent in the numerator is going to go downstairs into the denominator, and that one term with a negative exponent downstairs, x to the negative 1/2, is going to go upstairs. So we do that first. And of course the term with, or the factor with a positive exponent stays put. So y to the 3/4 stays y to the 3/4 because it's got a positive exponent. Now we're going to do two things. We've done enough of this in Math 100 where we did it separately. I think it's okay to do this as a single step here. Notice that we are going to subtract the exponents on x because they're in different places, one upstairs, one downstairs. And we're going to see that there are more factors of x, and that's the way we said it in Math 100. You can still say it that way. The exponent on the denominator is bigger than the exponent on the numerator. So we're going to end up with some x's downstairs. So this is a subtraction question. So get out your calculator, 5/8 minus 1/2, and that'll be your new exponent on x in the denominator. Now, similarly, the y's, that's a different rule because the y's are in the same place. They're both downstairs. So we're going to add those. So that's 3/4 plus 3/4. And for our final act, we'll clean up the exponent on the 2. 2 squared is 4. So when you do that arithmetic, you notice that there's more x's downstairs, so no more exponents or variables in the numerator. So that gives us a 1 up there. The 2 squared gives us a 4. When we subtracted those exponents on x, we saw 1/8 more downstairs than upstairs. And then we added the exponents on y. We got 3/4 plus 3/4, which gave us 6/4. So in our next step, we're going to simplify all this. Of course, 6/4 can simplify. 6/4, the exponent on y, is really 3/2. So we're going to rewrite this in a little bit nicer way using our friends, the radicals. So there's the 1/8 exponent becoming the 8th root of x. And then we simplified the exponent on y just using our skill simplifying fractions. You could use your calculator too to get that index of 2, exponent of 3. Now, formally, we're not allowed to have radicals in the denominator, so we need to multiply by a form of 1. So that's a question I'm leaving up to you what that is. And when I did that, this is what I got. I had to multiply by 7 more factors of the 8th root of x, and I had to multiply by 1 more square root of y to get those radicals outside of the denominator. That's called rationalizing, and that's an important skill, and we're going to do that when we get to complex numbers too. So that finishes this section, and I'll see you soon for those complex numbers in section 8. Stay safe and get in touch if you need anything. Bye for now.